Good morning, IB Math. 6.8, Law of Sires? That should be Sines, S-I-N. Oh dear. I don't know what's worse, my handwriting on these lessons or my handwriting on the chalkboard. Some of you had me in class for a while. I know my handwriting overall is pretty bad. Sorry about that. Anyway, here we go. Law of Sines. So law of sines is another quick little advanced trick that we can use with triangles that are not right triangles. So let's take a look at the law of sines. Now I'm going to try to draw a triangle that is obviously not a right triangle. No right angles in here. And I've got angles A, B, and C, and side lengths little a, little b, and little c. Again, just like in the law of cosines, notice that angle A, side A, angle B, side B, angle C, side C. Whichever is the biggest angle will be the biggest side. Whichever is the smallest angle across from it will have the smallest side, and so on. That's Pythagorean inequality, right? We should remember that from geometry. Now, the law of sines says that there's a relationship between the side lengths and the angles. Specifically, that the sine of angle A divided by the length of side A. So the sine of the angle over the length is exactly the same ratio as the sine of angle B divided by the side length across from it, which is in the same ratio as the sine of angle C divided by the side opposite from it. So these are all in the same ratio. A, B, B, C, C. Of course, I could flip the whole thing. It would be the same thing as the length of side A divided by the sine of the angle opposite from it is in the same ratio as the length of the side over the sine of the angle opposite, the same ratio as any length of any side divided by the sine of the angle opposite from it. Now, we have to be careful with this one, because in this particular case with law of sines, we're going to run into something called the ambiguous case, where there might be more than one possible answer here. So before we get to kind of jumping in on this, let's just take a look at a sample problem, just a simple basic problem. Before we talk about the ambiguous case and weird things that can happen, let's just take a look at a triangle. Suppose I have a triangle like this, and I'm going to tell you that this angle is 40 degrees, that this side is 6, and that this side is 8. And I want to find the missing information in this triangle. All right, so as I take a look at this, I'm going to pick, let's see, could I use law of cosines on this? I think I might be able to use law of cosines to find this missing side right here. But I'm going to use law of sines. If I can find one of those angles, I'm going to call this angle theta, and I'm going to find angle theta. And I'm going to use law of sines, and I know that the sine of theta over the side opposite is the sine of 40 over the side opposite from it. So the sine of theta is going to be 6 times the sine of 40 over 8. My calculator. Ooh, what mode do I need to be in here? Degree mode, right? So I'm going to check that. I was in radian mode, so I want to make sure I'm in degree mode. All right, so the sine of theta is going to equal 6 times the sine of 40 divided by 8, which is 0.48209-ish. Take the inverse sine of both sides, so the second sine of my previous answer, and I get 28.82 degrees approximately. So now I know this angle right here. Could I find that angle? Yes. Do I have to do anything fancy? No. I could find that angle just by knowing that the angles inside of a triangle are 180. 180 minus 40 minus this angle will tell me that angle. When I know that angle, can I find this side? Yes, using the law of sines. The sine of this over that equals the sine of this over that. So I could solve the rest of the triangle pretty quick and easy here. But what I want to do is I want to look at the problem with the law of sines. And this is something called the ambiguous case. Now, let's see if I can spell this right. Ambiguous case. Now, the ambiguous case happens it doesn't happen in the law of cosines. It's not an issue with the law of cosines. But the ambiguous case happens when I have a triangle, something like this, and I've got angle A and side B and little side A. But notice what can happen here. If I think about this little side A, if I extend this side, I could have little side A over here. And then I get an obtuse triangle with these measures, and I get an acute triangle with the same measures. Basically, I'm taking this side length A, and I'm kind of swinging it over there, the side length A. So I end up with two different possible triangles. I get the obtuse triangle, but I also get the acute triangle, where the angle A's are fixed, the side length B's and A's are also fixed. Now, in this ambiguous case, what would have to be true? Well, what about the relationship between sides B and A? Side A is the key here as I look in this. So here, I really have two triangles. Is it possible that I could only have one triangle? Yes. What would have to be true for side length A to only have one triangle? Well, if it was the horizontal right here, made a nice perfect, not horizontal, I'm sorry, vertical, the height right here, then I would get one perfect right triangle. Or if side A was bigger than side B, then it couldn't be in here. It would have to be out there. I would only have one triangle. So this is going to happen when side A is less than side B, but it has to be more than the perpendicular here. What if side A was ridiculously small? Then if it only came down to like right here and never made it down there, maybe I've got no triangles at all. That's another possibility. So this ambiguous case, it will drive you crazy. It will be very frustrating here. There is a relationship between these two angles because angle A is going to be the same in both. There's a relationship between the two angles here and the two angles there. Let's take a look at some examples now, including where we're going to have to deal with the ambiguous case. All right, so consider a triangle where I'm going to tell you, let's see, we've got A, B, and C, and I'm going to tell you that this angle is 30 degrees, and this side length is 10, and this side length is 7. So here, clearly, we have a case where it most likely is the ambiguous case here, where this side 7, I could swing it over here and create a whole nother triangle. All right, so I really want to focus on angle C here. One of the possibilities for angle C is going to be obtuse, the other one is going to be acute. So if I just plain old use my law of sines here, just kind of jump right into this and law of sines, I can say that the sine of 30 over the side opposite is going to be the sine of angle C over the opposite. In other words, 10 times the sine of 30 over 7 is the sine of C. On the calculator, degree mode, I want to make sure mode is, okay, degree mode, good. So 10 times the sine of 30, close parentheses, divided by 7, gives me 0.71428 approximately, take the inverse sine of that, second sine of my previous answer, and I get 45.58 degrees. That's one possibility. But what's the other possibility? Well, the other possibility is that this angle here, that angle C, could be 180 minus the angle, the opposite angle of the opposite side of 10 over 7, which would give me 180 minus what angle has a sine of, well, that's going to be more than 1, right? That's not going to be right. That has to be, oh no, 14, I'm sorry, 14, 10 over 14. 10 over 14. There we go. So the other angle, angle C, could also equal 134 point, oh, am I in degree? Yeah, I'm in degree mode. So I get two different possibilities for angle C. And then the best thing to do, if I had to solve and find the other angles in the triangle, would to be draw the two triangles out, one of them where angle C is that, one of them where it's that, and then I could use law of sines to find the missing side at the bottom. And of course, 180 degrees in a triangle, I could find angle B in both cases by just taking 180 minus those. All right, let's take a look at another sample problem. So let's see. Suppose I have suppose I'm on the top of a very tall building, and looking down to some fixed point, 40 degrees, and looking down to some other fixed point, 46 degrees, or if I'm on the ground looking up to the top of the building. And these 2 points are, let's say that they are 35 meters apart, and I want to know how high is the building. All right, so if I take a closer look at this triangle right here, I know that, oh, let's see, if that's 46, what's that angle inside there? All right, so let's see, 180 minus 46. The angle inside here is 134. So if I take a look, I'm just going to look at just this triangle here for a moment. And I know that that this length, I'm going to call this length y and this length z. And I know that y over the sine of 134 is equal to z over the sine of 40. Which is equal to this distance right here. Let's see, x, y, z. I'm going to call this distance w. W over the sine of, oh, what's that angle up in there? So again, I'm just focusing in on this triangle right here right now. What is that angle up there? So let's see, 180 minus 134 minus 40, 6 degrees. So this angle up here is 6 degrees, the sine of 6 degrees. All right, and let's see, what does that tell me? That and I know this length here. I know that this length is 35. So I'm not going to use this one. I'm going to use these two right here, or really I want to know Z for this triangle here. So I'm going to use these two right here, and I'm going to say that Z over the sine of 40 equals 35 over the sine of 6. So Z, this length right here, is going to be 35 times the sine of 40 over the sine of 6. All right, so here we go, calculator time. 35 times the sine of 40 divided by the sine of 6. And so this length is 215.229. So now take a look at this triangle right here. Let me just redraw just this triangle. (46x), and we just found out that that length right there was 215.229, and I want to find that. So now this becomes just a nice plain old sine problem, doesn't it? I've got an angle, I want to know opposite, hypotenuse. So just plain old sine of any angle is the ratio of the opposite side over the hypotenuse. Substituting in, the sine of 46 equals x over 215.229. So 215.229 times the sine of 46 equals the height of my building. So I'm going to take my previous answer times the sine of 46, and I get that my building is 154.8 meters high. All right, so let's see. I think that's pretty much a couple of sample problems there. The homework, problem number 1 is just basically solving parts of a triangle. Problem number 2 is an airplane is flying at a course that's and the 15-degree angle. Problem number 3 is a hot air balloon with an angle. And remember, the key is to draw the triangles. And these will be non-right angled triangles, but that's okay, don't worry about them. And then you're going to use the law of sines on these. Okay, so use the law of sines. All right, so now I want you to do homework 6H, which is on page 396, and I want you to do problems 1 through 3. And in each case, draw the triangle out and look for the law of sines and set up the law of sines. If you've got any questions, put it in the post section and we can talk about it. And we're going to be moving on and using some of these things to do things like finding the areas of triangles, the length of chords, the areas of sectors. This chapter is a very long chapter, but it's really broken down a lot into these smaller skills. So the lessons here, 15 to 20 minutes or less on most of them, and then kind of doing a bunch of problems. Normally in class we would do 2 or 3 sections every day. 2 or 3 of these little sections every day. Like certainly law of sines and law of cosines would have been a one-day lesson. All right guys, good luck, and I will talk to you again soon. Bye.